Hi guys, this is NTPhD Guy 1. In this video I'll be talking about the chi-square test, one of the most often used tests in statistics. And in particular I'll be talking about the formula it's used to define the test statistic for the chi-square distribution, that formula O minus E squared over E. And I hope this video will be useful to two groups of students, both the beginners who want a little bit more of an exposure to this formula, a few more practice problems, maybe a new perspective on why this formula is the way it is and why it works. And also to advanced students who would like a more in-depth treatment of why the formula is justified and why it connects to some of the other ideas you might be used to in stats. So before getting started, I'd like to point out that if you're just finding my videos to be incomprehensible or my interpretation just isn't working for you, then I would highly recommend Khan Academy's videos or basically any other video that's already out there on YouTube. Most do a really nice job of summarizing how you do the calculations and just the nitty-gritty of the chi-square test. But what I'd like to do in this video is just to cover this topic that it's kind of thrown at you when you take stats, that when you do the calculations, you just do the formula O minus E squared over E, and you just sum up everything, and kind of go over the justification for that. So first we'll try to come up with a good definition of the chi-square distribution. Suppose I have some random variable x, and that random variable is distributed according to the standard normal distribution. So recall that the standard normal is just a special case of the bell curves that you're probably familiar with mu, the mean, being equal to 0, and sigma, the standard deviation, being equal to 1. So up above I have a sketch of the standard normal distribution. So you can see most of that is going to be clustered near 0, and most of the time it's going to be between -1 and 1. And some of the more extreme instances like +5 is going to be right out here in the right tail, and like -10 will be way out here in the left tail. So now I've got my random variable x set up, just following that standard normal distribution. So what I'm going to do now is, let's say I have some computer program, let's say MATLAB, and I've got a program to give me numbers at random from the standard normal distribution. So what I'll have it do is when I press enter, it outputs some number. And then what I'm going to do, first let's call that number x1. So I'm going to take that number that comes out, and I'm just going to simply square it. And then that's going to create some new number, namely some new random variable, chi-squared. I keep doing that process over and over again. Have the computer spit out a random number, x1, square it to create the chi-squared value, and then you see what number is going to come out most often. So what I've got plotted down here is the sketch of the chi-squared distribution with 1 degree of freedom. So you can see here where chi-squared is near 0. That's the most likely value that you're going to get for chi-squared. Why is that? Well, because x1 is coming from the standard normal, so most of the data is going to be clustered around 0, so you're going to get a pretty small number. Then when you square that number, you're going to get an even smaller number, most likely. So that's why most of the data for the chi-squared distribution is going to be clustered down here where chi-squared equals 0. And as you increase the value of chi-squared, let's say maybe 5 is out here, well, that's going to be pretty rare, because in order to get that, you'd have to sample square root of 5 from the standard normal, then you square it to get 5 here. So getting that number square root of 5, that's going to be pretty unlikely from the standard normal distribution. What we've created from this process of pulling in some random number, x1, from the standard normal, and then squaring it to create chi-squared, is the chi-squared distribution with 1 degree of freedom. And this is the terminology you'll hear most often, the degree of freedom, which just means that we pulled one number from the standard normal and then squared it. So instead of picking one number from the standard normal distribution, let's try picking 3 numbers from the standard normal distribution. Let's call them x1, x2, and x3. So we do the same process. The computer outputs those 3 numbers, x1, x2, x3. We square each one of them and then sum up the squares to find our chi-squared value. So what's the distribution that you get out of that? So down here I've sketched the chi-squared distribution with 3 degrees of freedom. So you can see that the curve compared to the 1 degree of freedom is shifted toward the right. And this would be expected just because you're adding up a bunch of positive numbers, so that whole distribution is going to start to shift toward the right as the degrees of freedom increases. So one nice property of chi-squared distributions with degrees of freedom above 2 is that the mode, or the most frequent value, this peak right here, can be found just by subtracting 2 from the degrees of freedom. So here we have degrees of freedom equal to 3. So the mode is just going to be chi-squared equals 1 down here. So let's say we had a higher number for the degrees of freedom. Let's say 10 was the degrees of freedom. So that means the mode would be chi-squared equals 8. So that peak right there is always going to be at degrees of freedom minus 2. And of course that would be for for values with degrees of freedom greater than or equal to 2. So at this point, we can say that the chi-square distribution with n degrees of freedom would just be obtained by taking n numbers, x1, x2, x3, all the way up to x sub n, from the standard normal distribution, doing as we did before, squaring those numbers, and then adding up all those numbers to get chi-squared. And that would be the definition of the chi-square distribution with n degrees of freedom. And just like we did before, we'd get this sort of profile for the chi-square distribution, and its peak would be centered at n minus 2. So let's deal with some actual examples. So suppose I have a coin, and what I'm going to do is I'm going to flip the coin 10,000 times. I'm going to check and see if it's a fair coin. In other words, I want to see if the proportion of heads is equal to the proportion of tails, or in other words, just 50-50 for heads and tails. So in terms of figuring out what sort of distribution this will follow, in terms of the symbols, you're probably familiar with seeing that n is equal to 10,000, the number of coin flips is equal to 10,000. By hypothesis, the proportion of heads, p, is going to be equal to 0.5, and the proportion of tails, the failures, is going to be equal to 0.5. So you might know that when we do this sort of experiment, the distribution that's going to be followed approximately is going to be the binomial distribution. Specifically the binomial distribution with a mean of 5,000 and a standard deviation of 50. So why is the standard deviation 50? So we'll see here. So the formula for standard deviation sigma is equal to the square root of npq, which if you do the calculation, you get 10,000 times 0.5 times 0.5, take the square root, that's equal to 50. Furthermore, the mean mu is just equal to n times p, so that's just 10,000 times 0.5, which is 5,000. So that's fairly intuitive. So what we're going to do in this sort of experiment here, this hypothesis test, is that we're going to do the normal approximation to the binomial distribution. So since n is pretty large, this binomial distribution, binomial 5,050, is going to be approximated by the normal distribution with the same mean, 5,000, the same standard deviation, 50. So as I said, we're going to take the approach of approximating the binomial distribution with the normal distribution. So we have the exact distribution, the binomial distribution, binomial 5,050, and we're going to approximate it with normal distribution 5,050. And what we're going to do is just probably a test you're fairly familiar with called the z-test. So suppose we actually do the experiment and we get a number of heads equal to 5,100. So x is going to be equal to 5,100 in this experiment. So we're pretty used to doing this sort of thing. We then calculate the z-score, which is just the number that you actually get minus the hypothesized mean. So in this case, we have 5,100 heads, and we hypothesized 5,000. So the deviation there is going to be 100. Then we just take that deviation from the mean and divide by the standard deviation, which is going to be 50. So we end up having 100 divided by 50. So that means that we're two z-scores to the right of the mean. So in terms of hypothesis testing, I hope that was fairly familiar to everyone. So what I'm going to do now is I'm going to take that z-score that I just obtained, z equals 2. I'm going to actually calculate the value that we actually care about, the p-value. So in order to do that, I'm going to use this pretty nice website. Pretty much shows everything you'd want to calculate in terms of z-scores and other distributions. And what I'm going to do is just calculate the tail probabilities. So the sort of test that I'm doing here, it's overall deviation from equal numbers of heads and tails. In other words, I want this sort of calculation here, the two-tailed calculation. So I'm going to select this. I'm going to input the z-value that we just obtained, z equals 2. And then out comes the p-value. So our p-value for this experiment is going to be 0.0455. Now I'm sure most everyone's probably familiar with how to interpret these sorts of p-values. So in this case, the interpretation would depend upon what sort of significance we had set before doing this sort of experiment. So if we had assumed that we do what people normally do is set alpha equal to 0.05, since we got a p-value less than alpha, then we would reject the null hypothesis. And remember that the null hypothesis for this experiment was that the proportion of heads was 50%. So we would end up rejecting the null hypothesis and accepting the alternative hypothesis, which is that the underlying sampling distribution is not what we hypothesized. So at this point you might be wondering, what does this sort of test have to do with the chi-square test? I thought this video was about the chi-square test. Well, let me propose another way of looking at the same problem, now involving the chi-square test. So we're going to do the same experiment. We're going to flip the coin 10,000 times, and we're going to look at the proportion of heads and tails. So let's suppose the same sort of experimental result that we get 5,100 heads. So since we flipped the coin 10,000 times, that means we must have 4,900 tails. So our O row, one you're probably used to seeing O for observed, heads is going to be 5,100 and 4,900 for tails. So again, we're going to use the same null hypothesis, namely that the proportion of heads is going to be 50% and the proportion of tails is going to be 50%. So since we flipped the coin 10,000 times, we expect 5,000 heads and 5,000 tails. Now we're going to do that standard chi-squared calculation, where we're going to take the O minus E squared divided by E for each one of these comparisons, and then we're going to sum up the whole thing to get our test statistic. So just reviewing that. So for this cell right here, we have 5,100 heads observed, and we had 5,000 expected. So we take that difference, square it, divide by the expected, 5,000. So we have this calculation for this cell, and we just repeat it for this cell here, the tail cell. So we have 4,900, that was O, 5,000, that was E. Take that difference, square them, and then divide by E, which was 5,000. Then finally, we add those two values. So you end up getting 2 for this one here, and another 2 coming from this one over here. So our sum of chi-squares is going to just be 2 plus 2 being equal to 4. So we're going to say that our test statistic here, the sum of chi-squares, is equal to 4. And the underlying distribution here is going to be the chi-square distribution with 1 degree of freedom. So as we did before with the z-test, let's actually perform this hypothesis test with our, instead of using z equals 2 for the z-test, we're going to use chi-squared equals 4 and see what p-value comes out of that. So again, I'm going to use this calculation here. So I'm going to go to the chi-squared distribution. And the probability that I'm interested in is already selected here. So we're looking for this right tail probability, which is going to correspond to high deviations in chi-square. So we're looking at the rightward tail for this chi-square distribution. So I go here to this box, I input 1 degree of freedom, and our chi-squared value end up coming up to 4. So our probability, the p-value is 0.0455, and hopefully that number sounds pretty familiar. It's the exact same p-value that we got for the z-test. So for the rest of the video, we're going to try to explain why it is that these p-values are coming out to be exactly the same, at least for this sort of test, when we're comparing the z-test to a chi-square test. So before I go further, for those of you who are kind of new to this sort of calculation, you may be wondering why it is that the degrees of freedom is being set equal to 1 in this case. After all, we did do 2 calculations here. We got the 2 coming from this calculation. We got another 2 coming from here. So we did 2 calculations, but why is it that we're using 1 degree of freedom for calculating the p-value? So the most intuitive answer I can come up with for that sort of question is you can think of these two as the numbers coming out of the experiment. And the other thing you have to remember that when we did this experiment, we constrained the number of coin flips to be 10,000. So once you get a number of heads, the number of tails is already determined. So if I had come along and I told you, I'm doing this experiment, I'm flipping a coin 10,000 times, and if I also tell you that I got 5,100 heads out of that, you automatically know I got 4,900 tails out of there. So in a sense, there are 2 numbers here, but only one is really a variable. Because once I tell you this number here, I also determine this number here. Or you can also think of it as the other way around too. If I tell you I got 4,900 tails, that means I got 5,100 heads. So there's that sort of deterministic relationship between the number of heads and number of tails there. So that's essentially why we're using 1 degree of freedom, even though we've got 2 calculations being set up here. There's only one true variable here. The other one's kind of a parasite. It's being determined once the other one has been set. So now that we've dealt with a concrete example of using the chi-square test, let's abstract it a little bit. So let's think of the same sort of experiment. I flip a coin a certain number of times, and I get a certain number of heads and a certain number of tails. So let me call the number of heads I get out of this experiment A, and the number of tails B. And let me also call N the number of times I flip that coin. And we should know already that the number of heads and number of tails has got to be equal to the number of coin flips N. So that's why I place B being equal to N minus A. And that goes back to what I was saying before. Once I know the number of heads, and if I already know how many times I flip the coin, then I already determined the number of tails, and I can calculate that using N minus A. So just like in the previous case, we're going to be concerned with the sort of distribution that these variables are following. And what we're going to do is really focus on this one, I call it a true random variable, the number of heads A. So what sort of distribution does A follow? Well, we said before that the exact distribution is going to be a binomial distribution. But here we're going to assume that n is pretty large, so it's valid to use the normal approximation to the binomial. So as you're probably familiar with, this distribution is going to have a mean of n times p, the number of coin flips times the success rate. And I'm leaving p undetermined here. I'm not going to set it equal to 0.5. I'm just going to leave it as p. So the mean is going to be equal to np, and the standard deviation sigma is going to be the square root of npq, another formula you're probably familiar with. So what I'm going to do now is I want to relay all this stuff back to what we were talking about before about setting up the chi-square distribution in terms of thinking of it as sampling numbers from a standard normal distribution. But the problem is I can't just use this A as it is, because we know that it's not a standard normal. A is not following a standard normal distribution. Namely, it's following a normal distribution with this mean here, np, and this standard deviation, the square root of npq. So what I'm going to have to do is somehow tickle this distribution in a sense to get it back into a standard normal distribution, or at least set up another variable that corresponds with it that also follows a standard normal distribution. And that may sound super complex, but this is a calculation that everyone who's taken a stats class is extremely familiar with. So what I'm going to do, so I have this random variable a and the number of heads. What I'm going to do is I'm going to relate it to a new random variable called z. And you'll see why I call it z in a second. So I take the random variable a, I subtract the mean, and then I divide by the square root of npq. So what am I doing? I'm taking this bell curve here, has a mean of np, I'm subtracting np, so what's that going to do? It's going to shift it back toward 0. Because if you imagine what this looks like, this is going to peak at np, and I subtract np, so it's going to bring it back to 0, just thinking in terms of transformations. Furthermore, I divide it by the square root of npq. So what's that going to do? It's going to change the standard deviation back to 1. So you can think of that division by the square root of npq as another function transformation. You might be familiar with that from either pre-calculus or calculus. So what that's going to do is change the width of the curve, and like I said, it's going to bring the standard deviation back from the square root of npq, which it was originally. It's going to change it to 1. So basically summarizing what I just said, well, what does that transformation from A to Z do? Well, I've shifted the mean back to 0, and I've changed the standard deviation to 1. So I now know that Z, this new statistic, this new random variable, is following a standard normal distribution. It's mean of 0 and a standard deviation of 1. So this is where we can start to connect what we were talking about when we were setting up the chi-square distribution, coming from a standard normal distribution. So now what we're going to do is we're going to think of sampling from not the distribution A, not the random variable A, but sampling from this distribution Z. And I hope you can see at this point why I call it Z, because this is precisely the sort of calculation you do when you calculate the Z-score. So what I'm going to do is actually perform the chi-square test, not on A directly, but on Z. So Z is following a standard normal, so I sample from the standard normal. And I'm doing it once, so I have 1 degree of freedom. So what does that calculation look like? So our test statistic, the sum of chi-squares, is just got to be equal to this stuff that I got up here when I was setting up the definition of Z, just that whole thing squared. So in the numerator I get A minus NP all squared, and then in the denominator I get the square root of NPQ squared, which is just NPQ. And all this is just a really fancy way of saying that instead of looking at the value that comes out of A, what I'm going to do in order to calculate the test statistic, the sum of chi-squares, I'm going to look at what Z-score is produced by A. So I'm going to take that Z-score, and what am I going to do? I'm just going to square it. And by doing that operation, I found one way of calculating from the definition of the chi-square distribution what that test statistic has to be. Just based upon the definition. Shown in these calculations here is that just based upon the definition, I can come up with a way of calculating the test statistic that I care about, the sum of chi-squares, just based upon the definition. Let's pretend I've never heard of that formula, O minus E squared over E. So we know that just based upon the definition, this is a good way, at least for this test, of thinking about this test statistic. Just taking the Z-score produced from A and then squaring it. So if you go back to the concrete example that we're talking about, if you remember what the z-score was, that was equal to 2. And what is 2 squared? That's equal to 4. Where did 4 come from as well? That came from doing the stuff that we're normally used to doing that formula O minus E squared over E. So is this a big coincidence that they're both coming out to be 4? So of course I'm going to argue that no, this is not a coincidence, that there's an analytic relationship between the two calculations. So just repeating what I've done here in the abstract example, I've got a certain number of heads, certain number of tails. Remember I called that A for the number of heads, and the number of tails is just called B. So if I start to think in terms of the calculation I'm used to doing, the formula O minus E squared over E, how would I normally set this up in terms of doing that calculation? Well, I do it this way. I would just get this row, the observed row, which is A, as I said, for the number of heads, and then B for the number of tails. So how many heads do I expect? Well, I flip the coin n times. I've got a certain success rate, P, so that means I expect n times P heads. And how many tails do I expect? Well, I expect n times Q, number of coin flips times the number of failures, that number of tails. So now I've got the expected row. So now I just do the calculation that we're all familiar with. I have these two calculations here, one for this cell on the left and one for this cell here on the right. So I take this difference, A minus NP, the O minus E. I square that, divide by NP, which is the expected number of heads. So I've got that calculation for that cell. And for the other cell, I've got B, which is the observed number of tails, minus the expected number of tails, NQ. I take that difference, square it, and then divide by the expected number of tails, NQ. And I just proceed as we normally do. We would, in order to find the test statistic, the sum of chi-squares, we would just sum these two calculations here. This calculation here for this cell and this calculation for this cell. So we know that in order for this approach to be valid, to sum these two ratios, based upon what I was saying before, the sum of these two has to be equal to that z-squared value that I derived in the previous slide. So essentially, we've got to have this equality here between the two approaches. So I think we're at a pretty interesting point in the discussion now. We've seen that these two approaches have to be equivalent to one another. And if you just look at these in terms of symbols, it doesn't really seem, at least ostensibly, that they should be equal to one another. After all, this stuff here on the left side, this is z squared, as we're used to calculating, so we have a deviation from the mean squared, and then we're dividing that by the square of the standard deviation, or a fancy term for the variance, NPQ, and this is somehow going to be equal to observed minus expected squared over NP, which is not NPQ in this denominator here, plus B minus NQ squared over NQ, which is a different denominator than on the left side. So at least at first glance, it doesn't seem that they should be equal to one another. But let's show that they are actually equal to one another. So just to remind you, this is the statement that we're trying to prove, that these two approaches are actually equal. So the first step in this derivation, or this proof, is that we know that, as I was saying before, the number of heads plus the number of tails is got to be equal to the total number of coin flips. Or in terms of symbols, A plus B has got to be equal to N. So that means B has got to be equal to N minus A. So what I'm going to do here in the next step is I'm going to take that value for B, I'm just going to substitute N minus A. Now from here on out, I'm just going to concentrate on the right-hand side of this equation. I'm going to show this is equal to the left-hand side here. So I'm going to make that substitution. I'm going to substitute N minus A in for B. So just right there, N minus A. So I end up getting, in the numerator here, N minus A minus NQ, all squared. And now for the next step, what I'm going to do is I'm just going to rearrange these terms. Instead of writing it as N minus A minus NQ, I'm going to write it as N minus NQ minus A. So nothing has really changed so far. I'm just swapping things around. So why did I write it like this? Well, you can see here in these two terms here, when I group them like that, it's pretty obvious that the common factor is N. So for the next step, I'm going to factor out the N. So here I have N times 1 minus Q. But what is 1 minus Q? Well, another fact that I know is that P plus Q, the proportion of heads plus the proportion of tails, has got to be equal to 1. So what is 1 minus Q? 1 minus Q is just equal to P. So now what I'm going to do is just take 1 minus q and plug in p. So now for this ratio here on the right-hand side, I've got now np minus a all squared over nq. And you can see at this point that the numerators are going to end up being exactly the same. So I've just got these different denominators here. So that's actually going to be my next step. I'm going to rewrite this instead of np minus a all squared. I hope everyone can see that that's equal to a minus np all squared, just because you can factor out a -1, and -1 squared is going to be just 1. Okay, so we're now almost at the finish line. We've got the same numerator in both of these expressions. We have in the numerator a minus np squared over np plus a minus np squared over nq. So these two denominators are the only things that are really different here. And just to remind everyone, this top line is just a statement that we're trying to prove. Or this is a statement that, this is a statement we're trying to prove. So now, the last thing I've got to do is just combine these two ratios. So I hope it's pretty obvious that the common denominator between np and nq is npq. So how do I get a common denominator here? I just multiply it by q over q. So that's why I got this extra q here. And what do I do to this ratio on the right-hand side? Well, I just multiply by p over p. So I've got this extra p here. So you can see numerator is just q times that common quantity a minus np squared plus p times a minus np all squared. All over now npq, which is starting to sound pretty familiar with what we're trying to show, the denominator being equal to npq. So now, the second to the last step, so I've got this common factor, a minus np squared, in both of these terms. So I'm going to factor that out. I'm going to rewrite that numerator as a minus np all squared times p plus q. And that's still over npq. But now, to make one last observation, what is q plus p? Well, again, just remind everyone that we know that p plus q has got to be 1, so q plus p is also 1. So this factor here, q plus p, is just equal to 1. And then that's exactly what we're trying to show, that this expression here is just a minus np all squared divided by npq. So there's a Stanford professor who teaches engineering math, and whenever he completes a derivation or proof, he always asks the rhetorical question, where did we start, where did we finish? So I think that's a pretty good philosophy for whenever you do these sorts of derivation. What was it that we started with, and what did we end up with? Or basically, just an essential question of what we did in this proof is, what have we shown? So we've shown that this quantity here, a minus np squared over npq, which is also equal to the z-score squared. And remember that z-score was determined by whatever value came out for a, the number of heads. So we get some number of heads, a, calculate the z-score from that, and square it to produce this method of calculating the sum of chi-scores. And we've shown that that method is equal to, or it's equivalent to doing the traditional method of O minus E squared over E. So let's see if we can tackle another concrete example involving the chi-square distributions and its relation to doing z-tests. In this case, we've already worked with the example involving 1 degree of freedom, so let's try 2 degrees of freedom. So in this experiment, I've got 2 coins. I'm constraining the number of times I flip both coins, so I'm going to flip coin 1 1,000 times. I'm also going to flip coin 2 1,000 times. And then the experiment is pretty obvious. I'm just going to look at what number of heads come out of each coin and what number of tails come out for each coin. So in this particular case, let's suppose from coin 1 out of the 1,000 coin flips, I get 510 being heads, and therefore the remaining 490 are tails. So for coin 2, I get 520 heads, and therefore the remaining 480 are tails. So I think the hypothesis is also quite intuitive. So let's hypothesize that the coins have the same proportion of heads. That's to say that they're equally fair, that there's no coin that's giving more heads or less heads than the other one. So notice this isn't testing a hypothesis that they're both producing 50% heads, 50% tails. This is just saying that they're producing the same proportion of heads. So under that null hypothesis, I'm allowed to lump all the data together. Just take all the data I'm getting in terms of number of heads from coin 1, and then combine that with the number of heads coming from coin 2. So I can see that the total number of coin flips, which would be 2,000 because you get 1,000 coming from each, I get 510 heads coming from coin 1 and 520 coming from coin 2. So that means that the overall proportion of heads is 510 plus 520 over 2,000, which is equal to 0.515. So that's the proportion of heads. So since we know the proportion of heads, we also know the proportion of tails. So that's just 1 minus the thing that we got for the proportion of heads, 1 minus 0.515, which ends up being 0.485. So as I kind of interpreted before, there are really two really random variables here, and I've marked those by a star. So remember I said I'm constraining the number of times I flip each coin. So each coin flip is going to have 1,000 trials. So as I said before, if I tell you that I have 510 heads, and I also tell you that I flip the coin 1,000 times, that also means that, just by deduction, that I get 490 tails. Along the same lines for coin 2, if I tell you I have 520 heads, then I also know immediately that I have 480 tails. So in this case, this is why we have 2 degrees of freedom here. So these are the quote-unquote truly random variables here. So let's proceed as we normally would, or at least in the first example. Let's calculate the z-score associated with these numbers of heads. So this is going to be like the derived way of calculating the sum of chi-squares. And what I mean to say by the derived method is that we're going to adopt the method that or at least I'm trying to get you guys to think about, which is that instead of doing the traditional method of O minus E squared over E immediately, let's think of these two as the random variables, this 510 and this 520, or at least as instances of the random variable. Then what we're going to do is calculate the z-score associated with each one of those, square each one of those z-scores, and then just sum the squares together, and that's going to produce our chi-squared statistic, instead of going immediately for the formula O minus E squared over E. So just as a reminder, the overall P is equal to 0.515, and the overall Q is equal to 0.485. So let's think about the distribution that these two random variables are following, this 510, or at least a random variable associated with 510, and then a random variable associated with 520. So again, the exact distribution is a binomial, but let's approximate it as normal. So the normal distribution is going to be normal n times p, the mean. So the number of coin flips in this case 1,000. So I just have 1,000 times 0.515. So the mean is going to be 515. And then if you want to check the calculations, the standard deviation sigma is going to be the square root of NPQ. So it's going to be the square root of 1,000 times 0.515 times 0.485. So that's approximately 15.8. So we've established that both of these random variables here in these cells are going to follow this distribution here, or at least approximately. They'll follow the normal distribution with mean 515 and standard deviation 15.8. So now let's do what I was suggesting. Let's calculate the z-scores associated with each of those two numbers, the 510 and the 520. So what z-score do we get for that one? We get 510 minus 515 for the deviation from the mean over 15.8. So that produces negative 0.316. And the z-score for coin 2, that's equal to 520, which is the actual value, 520 minus 515, the mean, divided by the standard deviation, 15.8, and that just produces the opposite of the other z-score, just positive 0.316. So now how do we calculate the sum of chi-squares? Well, we notice that each one of these z-scores, z1 and z2, that if I define this quantity, z1 squared plus z2 squared, since each of z1 and z2 follows a standard normal distribution, which we've established a few minutes ago, then this sum right here, this random variable here, has a chi-squared distribution with 2 degrees of freedom, just because I have two instances from the standard normal being summed together, being squared and then summed together. So that means our test statistic, the sum of chi-squares, is equal to this quantity squared, negative 0.316 squared, plus 0.316 squared, which is equal to 0.200. In summary, by using our derived method, by looking at the z-scores produced from that number 510 and the z-score produced by number 520, and then just calculating the test statistic that way, what we get is 0.200 for that method. So now, just go back to our so-called traditional method for calculating the sum of chi-squares. Here's our observed data, just as a reminder. So now, just as practice, for those of you who are new to this sort of thing, see if you can calculate the expected numbers for each of these cells. So for that, you'll need those values of P and Q. So you can just go back to the previous slide for that. So maybe pause the video and then calculate the values for E, the expected numbers for each one of these cells, based upon those two proportions. Okay, so this is what I get when I do the calculation for the expected numbers for each one of the cells. So remember that value for P was just 0.515, and the value for Q was just 0.485. So we flipped each coin 1 and coin 2, 1,000 times. So it's just 1,000 times that value for P in this cell. Same thing for this cell. And then just that value N equal to 1,000 times Q, 0.485 for this cell, and the same thing for this cell. So this is what I get when I calculate the expected numbers. So now to calculate the sum of chi-squares in our traditional method, let's do as we normally do. We compare the observed. We do a cell-by-cell comparison. We compare observed minus expected, square that, and then divide by expected. So for example, this cell here, if we look at this upper left-hand corner cell, we have 510 observed minus 515 expected. So we have 510 minus 515 all squared in the numerator, divided by expected, 515. And then we just do the cell-by-cell comparison for each of the remaining three. So lo and behold, when I do this calculation, you get exactly what we got before, 0.200. So I hope from this video I've driven home the point that these two methods of calculating the test statistic, the sum of chi-squares, using both the what I call the derived method and then the traditional method, are really equivalent. And that if you want to think of what you're doing when you do the traditional method, is what you're really doing is looking at the z-scores. And I hope I've shown that both in a concrete sense. We've done two examples of that, and we've got the same numbers, but I hope I've also shown that in the abstract sense, at least for this style of chi-squared tests, for 1 degree of freedom. But what I haven't done in this video is show it in the abstract sense for when degrees of freedom are equal to 2. So I leave that as a challenge for you guys. So just do out the algebra and show that doing that calculation as we did before, taking z1 squared and adding it to z2 squared, produces the same value as when you do this. But do it for any arbitrary value of the number of heads coming from coin 1 and the number of heads coming from coin 2. So just as a hint to help you get started with that, you might want to think about defining some random variable, let's say A, for the number of heads coming from coin 1. And let's say, well, let's call it B, the number of tails coming from coin 1. And then some new random variable 2, let's call that C, for the number of heads coming from coin 2. And the value D, coming from, or the number of tails coming from coin 2. And then just do out the calculations, it's like we did before with degrees of freedom being equal to 1. And then just use those facts that you know, like P plus Q equals 1, and that the sum of heads and tails has to be equal to the number of coin flips. And you should be able to show that, just like what we did when the degrees of freedom was equal to 1. And what you're showing here is that these two approaches are also equivalent for this style of chi-square test. But another challenge that perhaps someone will be able to solve, or maybe I'll do an additional video on it, is that justify this calculation O minus E squared over E for other styles of the chi-square test. So you might have noticed that the style that we're doing right here, it could be tackled pretty nicely by just doing z-tests for proportions, or just doing a binomial style test. But the chi-square test is pretty versatile. You can do tests of homogeneity, a goodness of fit. So as a challenge, and I'll probably work on this myself, is justify this calculation for the other styles of the chi-square test, and show that this approach using O minus E squared over E can be connected back to the definition that we first talked about with sampling from some sort of standard normal variable. Thanks for watching my video. Don't forget to rate the video, give it a thumbs up if you like it, or if you think it was just absolutely atrocious, just give it a thumbs down. Also, don't forget to leave a comment below. Any questions you might have, any comments you might have, any critiques of the video, something I could have done better, any errors, or any suggestions for solving the challenge problems. And if you like the channel, subscribe. I should have some videos being made just about general math and science topics. And if you've got any suggestions for interesting videos I can make, either about any area of mathematics or about science, particularly something that's related to biology or medicine, feel free to leave that in the comment section below. So thanks again for watching, and see you next time.